Hello, my name is Ring Zhang, and I'm from Mid-Sweden University. First of all, I should thank the committee for inviting me to give this presentation to introduce our work. The title is Turn the triboelectric charge on the body into energy and signals. Here we're talking about the triboelectric charges on the human body. Triboelectrification, or namely contact electrification, is a very common phenomenon. And I think maybe all of us have done this experiment to rub a glass rod with silk. Or if you have kids, they might like to rub a balloon with hair to charge the balloon or the hair. But if you talk about our body, so we are wearing clothes, and when we're doing different motions, our skin will have contact electrification with clothes to charge our body. And if you look at the triboelectric series, we can find skin is actually has a very high positive charge affinity. Then when we contact with different surfaces, the skin will be positively charged. So let's say if you're patting on your hand with a surface, you'll get your hand charged. And if you connect your hand with the ground, and then you can conduct the charge to the ground. And that is a triboelectric non-generator. And we call it human body constituted triboelectric non-generators, in short, H-TENG. So what we are going to do is to study the roles of the human body and to study the applications. We proposed that the human body can generate charges, can conduct charges, and can store charges, because human body can be looked as a conductor, and it can also be looked at as a capacitor. For the application, first we will use H-TENG as energy harvester, then we can use it to transmit signals or to sense different body motions. What do? We designed two types of H-TENGs. First is a single mode. We just connect the body to the ground. The second is contact separation mode. So we actually formulate a circuit between the body and the sort of counter materials with electrode at the backside. So this is the two types of TENGs. So how it works? It works because the human skin acts very like a TENG component, where it has a high impedance epidermis or stratum, which is up to 10 megohm, and below that is low resistance, so dermis or tissues. So if it is very like a TENG component, which has high resistance polymer touched with low resistance metal. But how the charge, because our body is sort of covered by skin. So if it has high impedance, how charge can be conducted away? Because the skin has a breakdown voltage, DC breakdown voltage is 500 volts. But if it's AC, it's lower, it's 33, as we know. So in this way, we can make two hypotheses to study the roles of the human body. The first hypothesis is if the potential generated on one hand is higher than 500 volts, then the charge can penetrate the skin and transfer through the body and to the other hand. And if we touch with metal, then the charge will be conducted away. This is hypothesis one. This is a simple animation. The hypothesis two, we assume the body as a network of capacitor and resistor. So the charge will pass slowly through the body and accumulate to beneath the skin on the other end. And when the potential goes above 500 volt, then the charge will be released because it can penetrate the skin. And this is simple animation. And to verify the hypothesis, it's actually very simple. We have a different circuit. So here for measure current or voltage. So we have one hand connected to the ground, and this hand we just padding. Then you see that signals have been detected right after you padding the hand. That means the charge can pass through very fast. That verifies the hypothesis 1. For the hypothesis 2, we first charge the body by padding hand to build up the potential on the body. Then we conduct the charge away by tapping the finger to an electrode connected to the ground. Then we tap once, then release. Then you can see here the potential rebuild. And when you tap again, the potential drop down and rebuild again. So you need several times tapping or several steps to conduct the charge away. Here's the experiment. So we first pad in the hand. So you see the LED lighting, and after stop padding, the LEDs has been actually lighted twice. So here I start to pad, and stop, 1, twice. So that means after I stop padding, the charge has been conducted twice. This charge is passed slowly through the body and be conducted away. And this verifies the hypothesis 2. So now we know how our body act in the H-TENGs. And then the second is how we apply this H-TENGs. First, of course, we use it as energy harvester. And second is code transmitter, third is motion sensor. For type I H-TENG, the output power density is about 3 watt per square meter. And for type II H-TENG, the power density goes up to 30 watts per square meter. And you can use it to drive timer or drive a calculator. And because time is short, I skip this video. So then we proposed a HN10. H here means human body. HN, that we have many human bodies. How it works? So in the type I H-TENG, we have ground. A charge has been conducted to ground. That is because the Earth is a big capacitor, can accept the charges. So, and we also know our body, human body, is also a capacitor. So if we replace this ground with another person, then the charge generated on this body can be conducted to the other one. And the charge generated on the other body can be conducted to this one. So in this way, the charge can flow between the body, and we can generate electricity in this way. Experimentally, we have measured the open circuit charge, open circuit voltage, and short circuit current, and it shows it actually works. And the current is low because the capacitance of the human body is much smaller than the Earth. But if you have many bodies act at the same time, it might be higher. That is harvest energy. Then how can we use the H-TENG to make code transmitter? Well, here we have a code transmitter made of H-TENG is type 2. So if you pat your hand on your leg or somewhere of the part of the body, then you can send out signals like SOS, because you can have a short light period or longer light period. And we okay, this is dot, this is a dash. We talk about use Morse code. But however, it's sometimes not easy to identify if it's a short or long period lighting. So we redesigned the circuit, add more LEDs and use finger to make switch to produce dash or dot. And then we can have a more obvious signal for SOS. S is a dot, O is a dash. It's like more LEDs. Here I use Morse code to represent triboelectric non-generators. So I just make it faster. It can be used like a code transmitter. A third application is motion sensor. We know our body is doing motions all the time. You sit down on chair or stand up from chair. You produce signal, different signal. Yes, sit down and stand up. When you walk on the floor, you produce different signals, can measure it. You're typing all the time on the keyboard, and you produce different signals. And even you pick up a ball like a plastic ball, then you measure the signal. And also if you just simply grab your hair, signal can also be generated. That means we can detect signals from different body motions. But the human body is doing complex motions all the time. There are at least 9 big categories of motions, like flexion, extension, abduction, adduction, rotation, circulation. But do we have the possibility to identify or recognize these motions? Well, I think there's a chance, but however, our body is doing different motion at the same time. So that is very complicated. So what we have done now, we just focus on one motion instead of different motion at the meantime. How we do this? First, we analyze the different scenarios of the triboelectrification between the skin and clothes. So there are different processes. It can be simple contact separation, simple sliding mode, or it can from contact separation to sliding, or from sliding to contact separation. And also, if you're wearing shoes, walking on the floor, then you have an electrical induction. So this is very complex if you mixed up or doing these motions at the same time. But we don't do that. We just focus one by one. Here is an experimental result. We start with our head. Our head can do different motions, but the motion is actually done by the muscles of your neck. It's not the skull is no, it's the muscles. So the muscles can get contact with clothes, and that will generate the signals. And the signals have been measured different. Flexion, extension, and if you rotate different side, it produces different signal. Because if you can, of course, analyze the process of the contact electrification. And also the arms, different motions, you can sense it. And the signal is obviously different. And that means we can recognize it. An interesting thing is we have done the experiment. We have two different smartphones. We use finger because when we use smartphone, we tap in, sweep in, zoom in, zoom out, and it will produce different signal. And interesting things, if you use different phones, like big J here, as one is Samsung, one is iPhone 4S. So sweep in, sweep out. Then you have different ratio between the positive and negative peaks, and that actually can identify what phone it is. And also the difference can be measured on different fingers with tapping. For the lower limb, legs, foot, doing different motions, and these signals can be analyzed in detail, and also there's a possibility to quantify the signals. Let's say if we jump up, jump forward, and jump back, it's figure I, and all the signals, the ratios between the positive and negative peaks can be quantified. So we can analyze the difference between the ratios to identify what kind of motion you're doing, what kind of jump actually. And that makes us a big chance to recognize body motion. But however, as I said, the body doing motion, different motion at the same time, that will make signal even more complex. We need the help of machine learning or deep learning to solve the problem for real application. Here I would show how sensitive the motion sensor is. If you walk one step forward or one step back, then actually, if you walk one step forward, you have produced 6 peaks. If you walk forward one step back, you have produced 9 different peaks. So it can sense the body motions in very detail. For applications, we can think first is for these people who are experiencing gait or some other diseases. So for Parkinson's diseases, the shaking frequency can be measured simply based on the triboelectric charge on the body. And also we can predict how a wounded leg will be recovered back to the normal force, sort of quantitatively. And here's other examples to show how the difference of body motions can be measured. So if you Downy and dolphin clothes, if even you have wear different clothes, different materials, the signal, the shape, if you look at shape, they're quite similar. So we have possibility to identify it or recognize it. And we can also identify different shoes based on the signals. And for different persons, produce different signals. So in summary, we have studied the human body constitute the triboelectric generators, and we studied the human body's rules and discussed the applications. And that's all. We thank our colleagues, and we especially thank Professor Dongning Wang, Professor Yang, and Professor Hao Zheng for their collaboration. Thank you very much.